You know, it's wild how something like cold fusion can just grab everyone's attention, even when, well, the proof isn't all there. That's kind of what we're diving into today, the whole cold fusion thing. We've got this Wikipedia article, some scientific papers you sent over. We're going to unpack it all, the history, the drama, all the back and forth, so we can get past the hype, and really figure out what's what.
Yeah, it's interesting how that idea of room temperature fusion, it goes way back, even before anyone called it cold fusion.
For sure, like in the 1920s, those early claims, Paneth and Peters, they thought they'd done it, converted hydrogen to helium using palladium. Talk about shaking things up.
Yeah, they did end up retracting those findings, though. Blamed it on, like, background contamination messing up their helium readings. But it's still an important story. Shows how this idea, it took hold early on.
Yeah.
And it kind of foreshadows those issues with, repeating the experiment and getting the same results, which would keep cropping up in cold fusion research.
Right, like a warning sign, almost. Shows even the smartest scientists can get things wrong.
Exactly. And then you've got John Tanberg, Swedish scientist. Back in 1927, he claimed he fused hydrogen into helium. Used an electrolytic cell, palladium electrodes, the whole deal. He was so sure about it, he even tried to get a patent. A method for making helium and getting usable energy from the reaction.
A patent. Wow, he must have been pretty confident. So what happened?
Well, they rejected his application because, he couldn't explain the physics behind it all. And, well, Paneth and Peters had already retracted their similar findings by then. These early stories, they really highlight those recurring themes you see with cold fusion. Exciting possibilities, then disappointment, and always those questions about, did they do it right?
Yeah, seeds of doubt right from the beginning. But then, fast forward to 89, things get really crazy. Fleischmann and Pons, these two electrochemists, they just dropped this bomb on everyone. They say they've achieved cold fusion.
Yeah, they said they did it at room temperature. Using electrolysis with palladium and heavy water, reported this extra heat, said it had to be from nuclear processes, even claimed they found tiny amounts of nuclear byproducts.
It was like the whole scientific world exploded. Cheap, clean energy. I mean, who wouldn't get excited?
The media went nuts. Everyone was talking about it. It was like when they discovered high-temperature superconductivity, another one of those wait what moments that changed everything. But under all the excitement, some problems started to show up.
Okay, so let's talk about those problems. A lot of other scientists tried to do the same experiment, right? What happened?
Right. At first, a bunch of scientists tried to replicate their results, and some even said they were successful. But then those retractions started coming in. Like that group at Georgia Tech, they thought they detected neutrons, a classic sign of nuclear reactions happening. But turns out their detectors were giving false positives, just from being exposed to heat.
Oh, wow. So like their equipment was messing them up.
Exactly. And then there was that Texas A&M team. They had to retract their findings, too. It was a wiring problem in their thermometers, giving them the wrong temperature readings. And those weren't the only ones. Several other labs had to backtrack on their initial claims. All sorts of experimental errors or problems with how they did the experiment.
So more people tried it, more problems popped up.
Precisely. And as more researchers couldn't get that excess heat, the optimism started to fade.
I bet that's when the scientific community really started pushing back.
You bet. Things really changed in April '89, just a month after the announcement. The American Physical Society had this big meeting focused on cold fusion, and some really big names in physics, like Stephen Koonin. He went on to be Undersecretary for Science during the Obama administration. Well, he basically said the Fleischmann-Pons claims were dead.
Wow, dead. That's pretty harsh. What were their main criticisms?
They said the results just couldn't be replicated consistently. And there were some serious problems with Fleischmann and Pons data, too, like their gamma ray measurements. They were missing something called the Compton edge, which basically means their data didn't match what you'd expect from a real fusion reaction. It raised a lot of questions about, how they analyzed their results and the methods they used.
So the recipe, like we were talking about before, just wasn't adding up. But with all this going on, I'm curious, what was the government's take on this? Did they jump on board or were they skeptical from the start?
Well, the Department of Energy, the DOE, they put together a panel of experts in '89. They were supposed to look into these cold fusion claims. And their conclusion, no convincing evidence of cold fusion. They even said they shouldn't give any specific funding to research in that area.
So a pretty clear no from the DOE. Case closed, right?
Well, not quite. The story of cold fusion, it doesn't end there. The DOE did a second review in 2004, looking at research done since the '89 review. Came to pretty similar conclusions. But even with all that, the research continued.
Wait, so people kept looking into cold fusion even after two DOE reviews said it wasn't going anywhere? Why?
That's where it gets really interesting. It really shows you how powerful scientific curiosity can be, and the allure of making a groundbreaking discovery. There was this small group of researchers, really dedicated, who kept going with cold fusion, even after the DOE said no more funding.
That's amazing. I mean, imagine going against what everyone else in science is saying, what kept them going.
Well, if cold fusion did work, think about it. Clean energy, safe, basically unlimited. It's a dream worth chasing, even if it seems impossible. But it's not just that they really believe they're onto something, these researchers.
But how do they even pay for their research if the government's not giving them money? Who is?
That's a big problem for them. Most of the money comes from private sources, small foundations, even just people who think cold fusion could work.
So they're basically working with almost nothing compared to these big institutions.
It's a real David and Goliath situation.
Mm-hmm.
But they don't give up, and it's not just the money either. There's the whole reputation thing. Cold fusion researchers, they get laughed at sometimes. People are skeptical. And trying to get their findings published in those big scientific journals. Almost impossible.
Yeah, tell me about it. Remember that article you shared about the U.S. Navy doing research on this? I was floored they were even involved.
Yeah.
What are they doing messing around with cold fusion?
Right. The U.S. Navy's Space and Naval Warfare Systems Center, SPOR, they've been studying cold fusion for ages. Back in 2002, they even put out this massive report, 2 volumes, summarizing all their research and saying they need more funding to keep going.
That's crazy. I can see why the military would be interested, though. Imagine a submarine or an aircraft carrier running on cold fusion. Total game changer, right?
For sure. And it's not just the U.S. Navy. The Italian Agency for New Technologies and Energy, ENEA, they've been funding cold fusion research since Fleischmann and Pons made their announcement. They reported some pretty interesting stuff, too, like getting over 500% more power out than they put in into their experiments.
500%, that's huge. Any other countries doing this?
Japan had a big program back in the 90s, and India has started doing more research in recent years, so it's definitely happening all over the world, even if it's not really getting much attention compared to what most scientists are working on.
It's like they're in their own little science world. But let's get back to the science itself. You mentioned that most scientists think cold fusion probably doesn't work. Why is that? What are the main arguments against it?
The biggest problem is that cold fusion seems to break the laws of physics as we know them. You see, nuclear fusion means overcoming this huge force that pushes atomic nuclei apart. They both have a positive charge, so they repel each other, like trying to force 2 magnets together, the same poles.
Right, I remember that analogy from before. It takes a ton of energy to get them to stick.
Exactly. To get those nuclei to fuse, you need crazy high temperatures and pressures, like what you'd find inside a star or thermonuclear bomb. But cold fusion, it claims to work at or near room temperature, which just doesn't seem possible with what we know about physics. There just isn't enough energy to overcome that force pushing the nuclei apart.
Okay, I get the temperature and pressure thing, but what about those byproducts we talked about earlier? Neutrons, tritium, gamma rays. If fusion is really happening, shouldn't we be seeing those?
That's another big problem. Regular fusion reactions, they produce those byproducts in specific amounts. But in cold fusion experiments, they're either not there at all, or they're found in amounts way too small to match what fusion theory says should happen.
So it's like they're saying they can bake a cake without flour or eggs. You might end up with something cake-shaped, but it's not really a cake.
Exactly. That mismatch has made a lot of people skeptical. You can't just say there's excess heat. You need the evidence of those nuclear byproducts to back it up.
Yeah. So cold fusion has some pretty big scientific challenges. But I also read that this whole controversy really changed how science gets published and talked about at conferences. What happened there?
Oh yeah, big time. Back in '89, cold fusion was the hottest thing in science, literally. It had the most published papers of any field. Everyone was rushing to publish their findings, the good and the bad. But then things changed.
I bet once the scientific community started turning against cold fusion, it became harder to get those findings published.
You got it. Mainstream journals got a lot more careful, often just rejecting cold fusion papers. Or they demand a crazy amount of proof. It became really tough for these researchers to share their work.
So what did they do?
They made their own spaces to talk about it. The International Conference on Cold Fusion, ICCF, started in 1990. They've been meeting regularly ever since. It's a place for cold fusion researchers to present their work and connect with each other, without all the judgment from the mainstream scientific world.
That's really interesting. So this whole controversy basically created a separate group of scientists?
It really shows you how much science is about people and culture. It's not just about facts and data. It's about community, reputation, who gets to decide what's real science.
That's a great point. So this group of scientists, they kept going. But I also read that lately the American Physical Society has been a bit more open to talking about cold fusion.
Yeah, that's true. Since 2006, the APS has had sessions on cold fusion at their big meetings twice a year. It doesn't mean they agree with the research, but at least they're willing to talk about it.
That's got to be a good thing, right? Maybe it means someday cold fusion researchers and the mainstream scientific community can have a real conversation.
It's possible, but we got to remember what happened back then with all the hype.
You're right, big claims need big proof, and until cold fusion researchers can do that, they're probably going to stay on the outskirts of science. So where does this leave us? What are the key things we should take away from all of this?
To me, the most interesting thing is that it's still a mystery. Even with all the scrutiny and not having a solid theory to explain it, there are still these reports of weird stuff happening in cold fusion experiments. Excess heat, helium and tritium being detected, even claims of nuclear transmutations. It's like there are clues that something groundbreaking is going on, something that changes how we understand physics, but we just can't quite figure it out.
Like a science puzzle with missing pieces. But that's what makes science so cool, right? There's still so much out there we don't know.
Yeah, and even if cold fusion never actually works as a way to get energy, think about what we might learn along the way. Who knows what else we might discover while we're trying to figure out these weird results?
It's all about the journey, right? Not just the destination. Even if cold fusion turns out to be a dead end, the research could lead to breakthroughs in other areas. We've seen that happen so many times in science.
Totally, like those alchemists trying to turn lead into gold. They never did it, but their experiments helped create modern chemistry. It's exactly. Sometimes the biggest discoveries come from chasing ideas that seem crazy at first.
Yeah.
But let's take a step back for a sec. We've gone through a lot, the early stuff in the 1920s, the Fleischmann-Pons controversy, all the research that's still going on. What do you think are the big lessons we can learn from the whole cold fusion story? What does it tell us about science, the media, how the public sees all this?
That's a good question. I think one thing we learn is how important it is to be skeptical and to use really good scientific methods. Everyone got so excited about cold fusion. At first, the media hyped it up. Everyone wanted a quick fix for our energy problems, but it all kind of backfired.
It shows how even scientists can get caught up in the excitement and wanting something to be true. Sometimes that overrides the need to do careful experiments and check each other's work.
And what about the media? It seems like they really pushed the cold fusion hype.
Oh, they did. And it makes you think about how important good science reporting is. The cold fusion story, it was often presented as really simple. It either works or it's a hoax. But science is never that simple. There's so much more to it, so much uncertainty.
Yeah.
And the media needs to do a better job of explaining that to people.
I think you're right. People need to understand that science is a process, a journey, not just a bunch of facts. And sometimes that journey takes you down weird paths with unexpected turns and even dead ends.
For sure. And for everyone else, I think the cold fusion story shows why it's important to think critically. Don't just believe everything you hear, especially when it sounds too good to be true, and especially when the media is making a big deal out of it.
So to everyone listening, as you learn more about cold fusion, keep all of this in mind. Check out the sources, weigh the evidence, and decide for yourself what you think. Maybe you'll see it as this weird scientific thing, a case study in how science works. Or maybe you'll get hooked on those strange results, those hints that something revolutionary might be out there.
Either way, the cold fusion story reminds us that science is always changing. It's about asking questions, challenging what we think we know, and being open to the possibility that there's stuff we don't know. Who knows? Maybe someday cold fusion will go from being this fringe idea to being accepted science. But for now, it's still a fascinating mystery.
Well said, and that's our deep dive into cold fusion. Until next time, stay curious and keep those questions coming.